You very much for coming today. So let me start with asking you a question. When you look around in the seats here, what do you see? Probably people. And maybe it's because my background in computer science and then becoming a molecular biologist, what I see are trillions of cells grouped together, collaborating to form human beings. And they are actually little organic computers, that every cell is just an organic computer that runs off of software, DNA, and that they network together in an incredibly sophisticated way, even more sophisticated than computers, in order to give you all of your physical capabilities, but even your thoughts, your emotions, your memories, and probably even your consciousness. So it's a remarkably complex computer, but it's a computer nonetheless, and the parallels are so compelling that I could speak for that, for a day. So I won't get into it in a lot of depth, but I will want to draw some parallels for you to help you to understand a revolution that is coming in healthcare, that is going to yield miracle cures to things that were formerly untreatable or incurable. And this thing is happening right now. It's accelerating. We're getting a drip, drip, drip of miracle cures already. But this is going to become a steady stream, and it's going to become a deluge in the near future. And it's going to touch us all. And it's extremely exciting, and it's an extremely exciting, extremely positive thing that's going to happen to society and to us as individuals. Let's see, I got to figure out which one's plus here. That one? There we go. So my talk is basically about reprogramming the human computer. So let me talk a little bit about the differences between a regular computer and a human computer. So a regular computer works in base 2, or binary, or zeros and ones. It has two symbols that essentially make up all the commands for a computer. In your body, here's the first thing that's more sophisticated about it. Your cells operate in ACTG, 4 symbols, or base 4. But they still are organized, the software, the DNA, is organized into commands, and the order of that ACTG is what determines what your cells do. And these genes determine what your cells make. Are they making enzymes, proteins, things to secrete, light-sensitive proteins that turn into electrical signals that go into your brain, stomach acid, whatever it is, it's all encoded by genes. And even though the DNA is the same in every single one of your cells, it's a complete operating system. Right? You have a network of computers at your university here. We have one at work. Not every computer is doing the same thing. It's running different parts of its operating system as necessary. And that's exactly what your cells do as well. Each cell has essentially a manager, it's called the endogenous promoter, that knows which part of your DNA applies to that cell so that cell can do its job every day in that collection, those trillions of cells that make you up. So you could imagine, with this sort of view of human beings, if we could change that operating system, if we could modify that operating system, if we could update that operating system, we could make you work better. And you would be right. What could we do if we could go ahead and update that operating system and get rid of the defects? Or even improve the way that it works right now? But I think, let's focus on the defects first. Well, the question might be more, what can't we do, right? We're limited right now by our understanding of how genes work. Even though we sequenced the human genome, all it did was give us the order of that ACTG. But it didn't tell us what every single one of those genes did. And it also didn't tell us how they interact. But what it did was it unlocked a whole bunch of research that is yielding exactly that information. The driver genes behind all different types of diseases. And once we understand how those genes interact, we can couple that together with our ability to change that code in order to improve the operation and in order to mitigate those drivers of diseases and to essentially cure or treat diseases in ways that we never could before. This is way more powerful than other types of drug development modalities. And it really boils down to something called the viral vector. So the viral vector is quite simply taking a deadly virus, or possibly a deadly virus, cracking it open, and scooping out the viral DNA, those little snippets of code that take over your system and do something bad with it, We can throw that away, and we can put update code in instead. So instead of using, that carrying capacity, these viruses have been doing this for millions of years in your body, or in the humans' bodies. They've been essentially hijacking your cells by dropping little snippets of code in there, and doing what? Well, it's sort of the same thing that viruses do on your computer. They take over your computer for some malevolent purpose, something that doesn't serve you as the host, right? You as the human being. Usually, most viruses, all they do is they carry instructions to replicate themselves. Cold viruses, that's pretty much all they are. They hijack the system. They're so effective that when a cold virus gets into a cell, that cell is a goner. For sure, it's a dead cell. Because they will hijack that cell, and they'll make it use up all of its energy, all of its resources, all of its machinery to just make copies of the cold virus, and eventually it'll run out of materials and the cell just falls apart, and those copies of the virus escape, and what do? Go on to the next cells. And don't worry about that. Colds are only deadly if you don't have an immune system, right? Because your immune system is actually even faster. It can overtake that cold, and it's not a problem. And I'm going to tell you a little bit more about that when I talk about our HIV functional cure. But, that's the idea, is that these viruses have been carrying out this hijacking for millions of years. What scientists have discovered how to do is to hijack the hijacker, right? Viruses and updates on your computer arrive pretty much the same way, right? They usually come in over the internet or attached to an email, or you download them from somewhere, you run them, and then you click on there, OK to install, and you hope it's from a reputable source like Microsoft, Apple, Adobe, or somebody that you can trust, but it could be a virus. What you've done is you've unlocked your computer's DNA to whatever code snippet it is in there, and it's going to do what it's going to do. So a virus and an update really, sort of mechanically isn't any different on your computer. It's just its intent is different. Well, it's the same thing when we hijack the hijacker. So we crack open a deadly virus. And as a matter of fact, what AGT uses is HIV. Wow. And we scoop out the DNA from HIV, which is the AIDS virus. And we also scoop out all of its capability to replicate, because we don't want to create a new virus. What we want to do is use the delivery capabilities of that virus to deliver something beneficial to you. Now, on your computer, right, some of your software is actually, that you download and install, is to protect you from viruses. That's right. Viruses or updates can get rid of viruses. And that's exactly what we do with HIV. We can use it to treat viruses. We can get it to hunt down viruses in your body, change your DNA to mitigate that disease. So that's just one example, but the idea being is that reprogramming you is incredibly powerful, and we now have ways that are reliable in the clinic with all these different viruses that we can use for delivery, all these hijackers that we can hijack, that we can get to a wide variety of cells, and we can do a wide variety of things, and we're only limited by the delivery capability of the technology as it exists today and our knowledge of the drivers of disease. And guess what? Both of those things are doubling or more every year. And the cost of doing this stuff is cutting in half. That sounds like a virtuous cycle to me. It sounds like this is going to get better and better and better, and I can tell you from 10 years in this industry, it absolutely is, and it will continue to do. And what you can take away from this talk is that high tech has come to drug development, and it's going to follow high tech curves, and the bottom line is that if you can dream it, you can do it. You don't know when you're going to get there, because you don't know when you're going to understand how to unlock that thing. What the drivers are, what the interactions are in these diseases. It's incredibly complex. Your genetics are not just your DNA. It turns out we just discovered, recently that there's an epigenetic layer that alters your DNA. And then we found out that this stuff that we used to call junk DNA that exists between different genes turns out not to be junk. It turns out to be microRNAs that can vary hundreds of genes at one time. So it's really complex, and there's a lot of discovery that's necessary. But actually, there's a lot of low-hanging fruit that's already been characterized, and we already know how to work with it. And so there's a whole bunch of things that we can already address with the current technology in a very efficient way, and it's already happening. So what's the next step? So I've already explained to you essentially how this works, and hopefully I've convinced you that it does work, but let me give you some examples of how it's working today. So if you've been watching the newspaper, you may have heard that 2 CAR-T products have been approved. So these are examples of what are called cell therapy or a form of gene therapy. They're basically altering cells. We pull cells out of your body, we alter them with viruses, we reprogram their DNA to make them do something special, and then we put them back in your body. By the way, I don't see any timer around here, so I apologize if I go over. But anyway, so we put them back in your body to do various jobs in your body. And in the case of CAR-T, what we're doing is we're taking out T cells, which are the natural hunter-killer cells in your body that could wipe out anything. Anything that they turn their attention on, they'll kill. And what we do is we take any old T cell that comes out of your body, and I don't mean we, because this is other companies, but they put on, the way that it decides what to pay attention to is something called an antigen receptor. So you have these T cells, and you have an infinite repertoire of these T cells. You have T cells that are ready for anything. Diseases that you've never seen. As a matter of fact, most of the T cells will be born with you and will die with you, never having seen the disease that they were looking for their entire life long. But if they do meet that disease, they're amazingly effective. What they do is that antigen receptor will send some surface protein. It'll get excited, it'll eat whatever that invader is. Could be bacteria, could be a viral particle, it could even be a cancerous cell. And then it'll get excited and stimulated, and it'll go back to the lymph nodes, and it'll bring back an army of itself to attack any of the leftover invaders that look like the invader that it just saw. This is how it gets on top of a cold. Your cold is growing geometrically, right? But your immune system can replicate T cells so fast that if it didn't stop, your body weight would double in 3 days. Can you imagine that? That's how powerful your immune system is. And it is great at killing. So how do they use that in blood-borne cancers? Okay, CAR-Ts, there's 2 of them out there that have been approved in the last 3 months. This is how fast this is coming on. 2 incurable cancers have an 80% cure rate now because they can reprogram T cells to hunt down the cancerous B cells, because that's where these blood cancers reside. But they do it in kind of an odd way, and it's not really my favorite philosophy. We have a different philosophy at AGT in terms of how we treat cancer. Hopefully I'll get a moment to describe that to you. But basically, what they do is they take out these T cells that might have been for the cold or one for the flu or whatever. So they just take out a big pool of these T cells. And they put a second antigen receptor on there that's just looking for B cells. Then they put it back in your body, and they do exactly what you'd expect. They just wipe every B cell out of your body. And guess what? They take the cancer with it. It's highly effective. As I told you, some of these cures are 80%. In completely incurable cancers like pediatric, acute lymphoblastic leukemia, it's relatively curable in children. It's not necessarily a death sentence when you hear it at first, and it wasn't before. But a big percentage of those are incurable. Well, guess what? CAR-T changed that. It changed it in a profound way. And this is what you're going to see, not just in blood-borne cancers, but in every cancer. And AGT is on the cutting edge of this, and we actually have a project in cancer that changes this philosophy. The philosophy that we have is don't treat the immune system. The immune system is incredibly powerful, but also incredibly complex and sensitive. I don't like the idea that these dual-specific T cells could float around in your body for a long time. What happens when that other one gets stimulated and it replicates, right, in the lymph nodes, and it brings back an army of bispecific T cells that are also looking for B cells, the flu and the B cell? Who knows? I mean, you could be a ticking time bomb. And believe me, these companies are solving that problem with kill switches and stuff like that. But for me, that's a little bit of kind of like a spit and Band-Aids in order to sort of fix that problem. But hey, if it's the best you got, it's the best you got. So here's how I think that cancers are going to eventually be cured, and this is what we're doing at AGT. we can go ahead and reprogram your cancer instead of your immune system. We can make your cancer infinitely stimulatory to the exact T cells that surveil for cancer every day in your body. Here's some more news for you besides the fact that you're a stack of organic computers. If I didn't make you feel bad enough already, this next one will get you. Every single person in this audience has cancer. Big deal. Doesn't matter. You get cancer every day. Usually it's little, small occurrences of, single cells that stress out, that have had too much chemicals, radiation, stress, or just have aged out. And in trying to survive, they may go cancerous. And then you have these specialized T cells that mop them up like it's nothing. It's absolutely no threat to you. And as a matter of fact, my recommendation to you, if you want to avoid what we call cancer, which is actually solid tumors, is relax. All right? Stress is the big killer. So stress will diminish your immune system and increase your stress. All right? That's great conditions for disease. So relax. Meditate, whatever it does it for you, but don't worry about cancer. Okay, so relax after what I just told you. You don't have real cancer. You just have normal immune system mopping up problems in your body like it does all the time. So here's what we do, though. That immune system could be stimulated. Those specialized T cells, what happens is when a cancer turns into a tumor, what's occurred is that it's hit a critical mass point where it's growing faster than your immune system is able to chew it away. There can be lots of reasons for that. I can't say that I understand it all, or even much of it. But the bottom line is at some point, your immune system just can't get at it as fast. But it gets even worse. Cancer has evolved in the same way that everything has evolved. And cancer has discovered ways to disguise itself against the very immune cells that are supposed to be mopping it up. It throws what are called checkpoint inhibitors out on the surface, and these act as traffic cops that tell the immune system, hey, nothing to see here, move on by. I mean, it really has that effect. You've probably heard of some of them like PD-L1. That's a giant drug category for Merck. They have something called, somebody help me out here. Okay, nobody's gonna, okay. Well, they have a PD-L1 blocker, and there's another one from AbbVie. I mean, they're all over the place. But the PD-L1 blocker will go ahead and sort of shield that camouflage, that cell surface protein that's acting as a traffic cop. They put a monoclonal antibody on top of it, and it blocks it, and the immune system starts to see the cancer again. And in fact, it's that Merck drug that turned out that it pushed Jimmy Carter over the line from being untreatable to treatable and may have saved his life. That little teeny addition of just decloaking the cancer for your immune system and allowing the immune system to do its normal job instead of being faked out was something that made the difference between incurable and curable. So it's very, very powerful. But what we can do when we reprogram the cancer is much, much more. So we can go ahead and we can slip in things that just tell the cells to stop making those cell surface proteins. So we can go ahead and decloak the cancer. But even more importantly, we can convert a bunch of those cells into factories, basically, that create a little substance called a peptide that is stimulatory to the immune system. It will drive your immune system to 300 to 600 times its normal activity. And those cancers just melt away, and we're seeing that in mouse models right now. So I'm getting some signals that I got to wrap this thing up. So I'll go very quickly to my point. So you heard about 2 CAR-Ts? Well, when I saw this technology, I said to my friends, you're going to see a steady stream of miracles. You're going to see people getting out of their wheelchairs and walking. You're going to see blind people seeing again. The lepers will be cured. It really is that sort of nature. I mean, that's the power of this thing. And in fact, it's happening right now. Some of you may have heard of Luxturna. Luxturna was just unanimously recommended for approval by the FDA committee for treating a form of inherited blindness. It's so effective that a woman who is legally blind, who can't read, who cannot navigate a room without a cane, is getting her driver's license. And we have no reason to fear. She can actually see just fine. So don't worry that they're out there. I mean, that's miraculous, right? And that's what you're going to see in the future with gene therapy. A drip, drip, drip over this next year or so of these miracle cures, followed by a steady stream, followed by a deluge, followed by a point where you just wonder, what did we ever do? How did we live without gene therapy? It's going to be like your cell phone and GPS and the internet. You're going to forget the day that you had it. You're going to be telling your grandchildren, we used to treat cancer with ionizing radiation and deadly chemicals. We used to poison you, hope the cancer died, and then you recovered. Well, that kind of treatment for cancer is going to go the way of bloodletting and leeches, I promise you. I've seen the pattern. It all has to do with the high-tech nature of this. The capabilities keep increasing. We're going to address more and more diseases. We're going to find effective cures for things that are nothing short of miraculous. The costs are going to keep going down. It's going to absolutely change healthcare forever for the better. And it's a very exciting future that we're going into. Thank you.